Hello, myself Dr. Lakshmi Devi, Professor, Department of ECE, St. Peter's Engineering College. Let us see first what's meant by the morphology. Morphology deals with the form and structure of animals and plants. Mathematical morphology, how it is correlated with the morphology of animals and plants. Let us see here. Using set theory concepts as well as extracting of image components, representation and description of region shapes of the objects from the images. We are concentrating on these aspects for extracting of information from the images. This word morphology commonly denotes a branch of biology that deals with the form and structure of animals and plants. The same word here in the context of mathematical morphology as a tool for extracting image components that are useful in the representation and a description of regions shape such as boundaries, skeletons and convex hulls, etc. Here we are also interested in morphological techniques for pre and post processing. Before starting the actual image processing, a few steps pre-processing and after completion of image processing, post-processing steps are there. In both the cases we can use these morphological techniques such as morphological filtering, thinning, pruning concepts. And let us see here the preview of this morphological methods using set theory concepts. Sets in mathematical morphology represents objects in an image. Let us see here, the background of the image appears to be the black and foreground objects appears to be the white. That white objects appears as set concepts in the morphological processing. Binary image, the elements of a set is the coordinate xy of the pixels that we are representing the set theory concepts with the Z square. Similar thing in gray level images, the elements of set is represented with xy, gray value. The amplitude of that particular pixel coordinates we are representing with the gray value, and that thing we can express in the set theory as a Z cube. So what are the topics we are going to cover in today's presentation? Means under the set theory, first you can see the introduction of set theory in order to understand the morphological processings in image processing. The main concepts are dilation and erosion, opening and closing, hit or miss transformation, some basic morphological algorithms and extensions to grayscale images. So preliminaries of set theory in the sense A be a set in Z square. A is the original image if we have represented, where we are representing image as f of xy as a two-dimensional coordinates of xy, and f is an amplitude of that particular coordinate of the location xy, that we are representing the set theory concepts as Z square. Just now we discussed that. Suppose let us take here A is equals to A1 comma A2 is an element of A. That is, A is an original image. That small a belongs to the original image of capital A. That locations are A1, A2. In general, we are representing with the spatial location of XY on two-dimensional image concepts. A is not an element of A. A is a location or the pixel appears in the original image of A. That's the meaning of A is not belongs to the capital A. So of course, null is an empty representation with a phi. Then set theory, explicit expression of a set theory, how you are representing means capital A is equals to A1, A2 and so on AN, which are different pixels in the set theory concepts of original image A. That how you are representing as a mathematical representation or equation point of view, A is equals to elements which belongs to the condition for set elements. Example, let us see here, C is equals to W slash W is equals to minus T. For D belongs to capital D. that is W/W or elements in the particular set belongs to the minus D, that D belongs to the overall defining area of a capital D. That's the representation of a mathematical equation. Let us see the set operations here. A is a subset of B. You know, in mathematics, as a mathematical students, how you are representing A is a subset of B. That is the representation. A is an element of another set B. Every element of A is an element of another set B. That's the representation. A subset of B. Union, A union of B. Intersection, A intersection of B. Mutually exclusive, A intersection of B is always a null. Then, a language of mathematical morphology is a set theory. So in this, just you can see all are binary images only. A and B's are two different types of objects, and how you are representing that set theory concepts on these two objects of A and B. A union of B is second image B, and third image A intersection of B. The common point in between the A and B is an intersection we are showing. And fourth one, that is D image, is A's complement. A's complement in the sense complement by neglecting the A, the remaining whole image is appears. That is A's complement of overall image. Then E image showing A minus B. That is subtracting of B from A is A minus B representation. These are some mathematical morphological concepts in the set theory. Next, graphical examples A union B, A intersection B. This already we up in the last slides. How you are representing that in the mathematical set theory concepts? A's complement is equals to W/W not belongs to the A, because A's complement is totally complement of the A. That's showing actually A's complement. A minus B means subtracting of B from the given A, that we are representing with the A minus B is equals to set of W/W belongs to the A, but W is not belongs to the set of B, because B we have subtracted from the set A. Basic set operations. These are some examples of basic set operations. Might be you are in a position to understand exactly the concepts what we are showing here. Translation of A by Z. Z is actually the location we are representing with the Z1, Z2 coordinates here. Z2 and Z1 coordinates. And this one is the A, which is represented here, A. And this is translation of A by Z. So by Z of Z1 and Z2 coordinates, if we have translated, this is actually represented with the A suffix of Z. This is A translated by a Z. Then reflection of B, the set A and B are from figure 9.1. Of course, here the B is, this is actually the shape of the B. This is the shape of the B. And reflection of the B means exactly opposite. That means if you are considering this one in opposite way from here to here, and that is the reflection of B, that we are showing B cap. Reflection of B is a B cap. This one is exactly opposite of this one. With this particular coordinates, it is showing above of this portion, that is a B cap. Okay. Translation A of Z, that is already we come across translation represented for A of Z. C/C is equals to C/C is equals to A plus Z, for A belongs to Z. This is actually the representation of AZ. This is already covered. Okay, we'll continue with the next. A of Z is equals to C/C is equals to A plus Z for A belongs to A. This is already discussed in the last slides, how we are going to consider the translation of A by a Z. This is a reflection. A reflection, how you are representing means, just in the last slide with the small figures I have explained already. B cap, we are representing this as a B cap is equals to W slash W is equals to minus B, which is represented as a reflection of that. But B belongs to the B. This minus B is the reflection of that B. That B belongs to the set B. That's a representation of a reflection. Then this is an actually different logical operations on morphological images point of view. A and B. A is an image and B is an actually a structuring element if you have considered, or another set. Then how you are going to perform a different morphological processings here with the logical operators. Logical operations like not of A, not of A. A and B are the two different types of images, means A and B, and operation of A and B. This is an actually A intersection of B also. A and B, or operation in between these two is A or of B, that is equals to A union of B. A and B is an XOR operation, gives an opposite of this AND operation. Here this is an XOR operation. And A and B are the two different images, and not A and that means this is not A, means A is absent here and the remaining part of the B appears here. This is an actually the operation, and B, this is an actually the operation of not A and B. So these are the different morphological operations representation as according to the set theory concepts. Let us see now. Binary images may contain numerical imperfections. In particular, the binary regions produced by simple thresholding or distorted by noise and texture. This morphological image processing pursues the goal of removing these imperfections by accounting for the form and structure of the image. These techniques can be extended to grayscale images also. So binary, what's the reason for going for morphological image processing? Means the goal of removing the imperfections appears in either binary images or grayscale images. That's a basic reason of going for morphological image processing. These are the different structuring elements. Structuring element based on the type and based on the shape of the structuring element, we are going to extract the objects from the original images. Examples of structuring elements here given. This one is actually the plus, or you can say it's a cross. And this is the structuring element of square shape. This is the structuring element of a vertical shape. This is the structuring element of diamond shape. How you are representing these structuring elements as square or rectangle shapes, in the sense by fulfilling the leftover pixels locations with white pixels. With white pixels, in the sense here, these are the black and these are the white pixel locations. There is no chance to have any locations of white pixels here because it's a square matrix, square structuring element. And this one is a rectangular structuring element, no need to have any that. Vare, Chinnu, itra. Let us see the different structuring elements and its operations here. Structuring elements can be any size and any shape. So here this is a 3 by 3 structuring element, and this one is a 5 by 5 diamond shaped structuring element. This is a 3 by 3 cross structuring element. Here this one is actually the structuring element 3 by 3 all are ones, and this one is an original image, and this is another structuring element of cross. How we are going to perform the operations of these structuring elements, morphological processing of structuring element over this particular input images. Now I would like to observe with the different examples. So A and B are two sets, then union A union B intersection A intersection complement AC and difference A minus B. and here represented the difference and or not operations. These are the different examples of that. This one foreground image is actually the white letters UTK reverse, and this one is the background is a black, and this one is also background is black and foreground GTs. And if you have considered this one, what is the operation of this one? This one is an actually the complement of this. That's the reason this appears to be black, the total background appears to be white. This is a complement of this image. And next, morphological image processing produces more stable segmentation results, including connected segmentation boundaries. This approach also provides a simple framework for incorporating knowledge-based constraints in the segmentation process. And this morphological processing, image processing, contain numerous imperfections. Binary images may contain numerous imperfections. That imperfections gets minimized with this morphological image processing. A simple thresholdings are distorted by noise and texture in the binary images, but in morphological image processing, basic reason or goal of this morphological image processing of removing of these imperfections. These techniques can be extended to grayscale images also. By choosing the size and shape of the neighborhood, you can construct a morphological operation that is sensitive to the specific shape and size of the input image. Morphological techniques probe an image with a small shape or template called structuring element. The structuring element is positioned at all position locations in the image and it is compared with the corresponding neighborhood of pixels. Some operations test whether the element fits within the neighborhood, while others test whether it hits or intersects the neighborhood. Fit or hits. That operations with the examples we are in a position to understand that operations. Probing of an image with a structuring element. Let us see here. A, B, C. These are the three structuring elements chosen here. A, B, and C. A is the structuring element which fits the image, and B is the structuring elements which that's element hits the image, intersects. Only the certain portion of an image is an actually intersecting with structuring element. Okay, let us see here. Structuring element. So fitting and hitting of binary image with the structuring elements S1 and S2. With this example, just we are in a position to understand how it is. Let us consider this one is the original image and S1 is one structuring element, S2 is the another structuring element. With this A, B, C, three different locations here we are giving, and whether these three locations, how this fit and hit operations gets taking place, we are observing with these two structuring elements of S1, S2. Fit S1 with A. S1 is all or ones with A, this is the location. A location also having all or ones. So fit S, that's why S1 with the A is yes. Then with the B, B means this is the location. Because here it's a 0 and here it's all or ones. That's why there is no any fit operation to be satisfied for the location of B. Then coming to the location of C, C is all elements or zeros except this top left corner of 1. That also no fitting operation satisfies. So no. So coming to the structuring element S2 for the fit operation. S2 1 1 1 1. This is the cross elements having ones. The remaining corner elements are zeros. Now the cross elements here get satisfied with the structuring element with the location of A. That's why S2 with this location of A is S. That means it fits this particular ones in these locations. We won't bother about the location of zeros. We'll bother about only the ones. So coming to the B is an actual location here. This 1 cross 1 cell gets satisfied with the structuring element 1s of S2. That's the reason S2 structuring element with the B location is also fits. Yes. Then coming to the C location, because C location all are zeros except this top left corner, sorry, bottom left corner. That's the reason there is no fit operation to be satisfied for the C location. So no. Coming to the hit operation, S1 with this location A, S1 with the location A, hit in the sense, this all are ones in the sense, there is no question of actually neglecting any of the pixel locations, so hits. Then coming to the B location is also for this S1 location. Here hits in the sense any one element is also overlapping with the same element, same value, then we'll call it as an actually the hit. That's why this particular B location with the structuring element is the structuring element of S1 is also S. Then coming to the C location with the structuring element S1, this particular one is matching with this one. That's why hit operation gets satisfied with the C location also. Yes. Okay, previous. So the most basic morphological operations are dilation and erosion. Dilation adds pixels to the boundaries of objects in an image, while erosion removes pixels on object boundaries. These are the basic two operations in morphological image processing. One is the dilation and erosion. Dilation adds pixels to the boundaries of objects. Erosion removes pixels on object boundaries. The number of pixels added or removed from the objects in an image depends on the size and shape of the structuring element used to process that image. Dilation and erosion are basic morphological processings, produces constructing results when applied to either grayscale or binary images. The dilation we are representing with the symbol plus and erosion we are representing with the symbol minus within a circle. Morphological operations on binary images. So white pixels are normally taken to represent foreground regions while black pixels denotes the background. This is not actually common for all the cases, but if you have considered in one case, with that procedure only we are going to observe the operations of this dilation and erosion. In some implementations, the conversion is reversed. That's the meaning of representing. It's not common for all the cases. White pixels are normally taken to be a foreground and black pixels are normally to be considered as a background. The basic effect of operator on a binary image is to gradually enlarge the boundaries of regions of foreground pixels. That's the white pixels typically. Thus, area of foreground pixels grow in size while holes within those regions become smaller. This is actually the dilation operation. How we are going to perform means the boundaries pixels gets increased in the sense, is there any chance to have holes in between an objects? Because of enlarging the boundary regions, there is a chance to minimize the holes within an objects. That's the meaning of representing here. Regions become smaller. It will expand the image. Dilation is the reverse process. Dilation is a reverse process with the region growing out from their boundaries. Already we come across in the image segmentation region growing concept. Based on the seed point, how we are going to increase the region, this particular dilation is the reverse process. We are not considering any seed points, but based on fit and hit conditions, we are going to enlarge the boundaries with the dilation operation. Dilation is an XOR operation of image A with the structuring element B. Dilation of an image F by structuring element S. Suppose if you consider input image is F and structuring element is S. How we are going to denote the operation of dilation means F dilation with the S. Produces a new binary image G is equals to F dilation of S with ones in all locations xy of a structuring element's origin at which that structuring element S hits the input image F. That is, g of xy is equals to 1 if S hits F and 0 otherwise. Whenever structuring element is actually hits F and 0 otherwise. G of xy is equals to 1 if S structuring element hits F, otherwise it's 0. The same process will be repeating for all the pixels of the image by a masking process with the structuring element over the input images. Dilation has the opposite effect to erosion. It adds a layer of pixels to both the both the inner and outer boundaries of regions. This is an example of binary image of dilation. So let us observe this is actually the input image as a binary image. With the dilation operation, we are observing here thickening the regions of each and every line of these characters. With this, the white pixels at its boundaries, it's enlarged. Because of this, the thickness of this each and every character increases here. With this, is there any bridging gaps in between the letters that will be minimized with this particular dilation operation? Let us see another example. Results of dilation or erosion are influenced both by the size and shape of structuring element. This dilation and erosion are dual operations in that they have opposite effects. Let us see here, FC denotes the complement of an input image F. The image produced by replacing 1 with 0 and vice versa. Formally, the duality is written as F dilation with the structuring element S is equals to F complement of F with the erosion of S rotation. That is, structuring element, if we have taken the rotation and do the erosion operation with the complement of the input image, that's equals to the dilation operation of input image F with the structuring element S. This gives actually the relation. This gives the relation of relation between dilation and erosion. You should remember this formula: dilation and erosion. S rot is the structuring element S rotated by 180 degrees. If a structuring element is symmetrical with respect to the rotation, then S rot does not differ from S. If it is symmetrical, there is no any effect of S with S rot. In a binary image is considered to be a collection of connected regions of pixels set to 1 on a background of pixels set to 0. These regions and dilation is the fitting of structuring element rotated if necessary into the background, followed by inversion of the result. In the morphological dilation and erosion operations, the state of any given pixel in the output image is determined by applying rule to the corresponding pixel and its neighbors in the input image. What are the rules for this dilation and erosion operations? Dilation, the value of the output pixel is the maximum value of all the pixels in the input pixels neighborhood. In a binary image, if any of the pixels is set to the value 1, the output pixel is set to 1. Erosion, the value of the output pixel is the minimum value of all the pixels in the input pixels neighborhood. In a binary image, if any of the pixels is set to 0, the output pixel is set to 0. I'll explain this on paper for better understanding afterwards. Let us see here morphological dilation of a binary image. And this one is actually a structuring element 111. This is an input image. How we are going to replace this with the center element of structuring element means 100 or the basic pixels in an input image. the structuring element is 111 elements. Structuring element consists of 111, and whenever we are overlapping the structuring element over this input image of 100, so here the maximum value of this structuring element, the maximum value of this input image gets replaced with the centering element. That's why here the centering element gets replaced by the maximum value of this as a 1. In this way, the morphological dilation operation gets taking place. And this one, grayscale image. If it's a grayscale image, means it won't consist of zeros and ones. It consists of 0 to 255 gray levels for 2 power 8. That is, the depth of the pixel is 8 bits. In that case, 0 to 255 gray levels are there. In that, structuring element, suppose 111 are their structuring elements. In this 16, 14, 14 or the pixel values of the original image, whenever we are overlapping of structuring element over these 3 pixels of an input image, the center pixel value gets replaced by the maximum value of this particular 3 pixel locations, that is 16 here. Center pixel is also gets replaced by 16. This is the way to do the dilation operation on grayscale images. Dilation in MATLAB. The MATLAB programming, how we are going to perform this dilation operation, that syntax here given. Image dilate A, B. A is an input image, B is the structuring element. So dilated image we are representing with the Y. This is the statement for programming dilation operation with the A image and B structuring element. And structuring element in MATLAB, they can be easily created using strl function. So that is structuring element strl shape parameters if you have given. Accordingly, it will generate the structuring element. Shape can be a diamond. Here we can represent in place of shape. Already we observed diamond, square, disc, line, etc. Parameters based on the size here you can specify. Accordingly, it will set the structuring element. With the strl command word, we can complete the programming with this particular statement. Structuring element creation with this strl operation by specifying the shape and parameters. Dilation operation, a mathematical equation is A dilated with B is equals to Z belongs to the set. This one is actually the reflection of Z. B is a reflected Z. Intersection of A is not belongs to the null. It's not belongs to the null means there is a chance to have some common points in between the intersection of this reflection of structuring element with this particular input image A. This is actually the structuring element B. This is the structuring element because of a square structuring element and symmetric around this origin. That's the reason B cap is equals to B here. The size of the structuring element is D by 4, D by 4. And if we have considered the input image size as a D as a squared image, D by 4 is the quarter of the size. Here we have this structuring element. Okay. So if we do the dilation operation with the structuring element over the input image and processing this structuring element around its corners like this, and there is a chance to mention this particular center of the pixel of the structuring element as a border, as a region here, that is the reason for coming this particular dotted line within this original input image. But this is actually the original input image, and because of this dilation operation, what happens actually the size of input image, it gets enlarged. Enlarged means this is actually the enlarged portion or extended portion of original image of size D by D. But D by 4 is actually the side of structuring element. D by 4 by 2 means this is D by 8. This portion D by 8 is only extended on all the corners, on all the surfaces of this particular input image. This is the dilation operation with the structuring element of this on this particular input image of A. Another formulation of a dilation with the structuring element, D is the length of the structuring element, D by 4 is the width of the structuring element. If we do the operation of the structuring element over the input image of D by D size, and this is actually D by 4 size results. and this one is d by 4. D results of this extended portion on top and bottom of the portions of this original image. And this one is the same, explained already. And this is another example of dilation, which is used for bridging the gaps in images. Here this is an original image observing in each and every character having some gaps in order to fulfill the letter fully. And here YEAR, EA just if you observed on a zooming portion. So here having some gaps in between the letter. Okay, that we can fulfill with this particular dilation operation with this structuring element. Then here it's not visible. This bridging gaps will be filled with this particular operation of dilation. An example. Dilation, just here we are representing with the dilation operation on set A and B are defined by this particular mathematical formula according to the set theory, and this is another example of A is the structuring element, sorry, A is the input image and B is the structuring element of this, and whenever we are moving this structuring element B over the input image, these are the portions gets extended of this object. This is the extended portion. Okay, that is A dilation of B. Enough here, this example. Then coming to the another dilation example, this is an input image. Dilation with a discrete disk. Discrete disk, the origin being inside of it, gives an isotrope swelling or expansion of the image. Note that here the white pixels have been chosen as the object pixels. Here white pixels are objects and background as black. So white pixels here enlarging over the input image, which increases the size of the object here. This is an actually dilation of an input image, resultant of dilation. And this is the difference between the original image and dilated image. This one is the difference. This is the extended portion of an actually original object. This is an example here. It clearly shows with the increasing of dilation, with the dilation operation, it increases the thickness of this particular characters, which minimizes the gaps in between the letter. Okay. This is another example of dilation. So here A is the one set and B is the structuring element. B is the structuring element, and here if you do the dilation operation of this, this is an actually the background of an image. Here this is an actually the foreground appears to be black, here background appears to be white. So in this, if you do the structuring element by considering this as a structuring element, if you do the operation of dilation over it, sorry, this one is an actually erosion operation. Adding of just a structuring element is set added with the background elements to form a rectangular shape, provided a background border. Structuring element as a rectangle. Here structuring element is this one is a cross processed by structuring element. With this process of structuring element, wherever there is a chance to have mapping of exactly this cross over it, just if I have placed here, this one is actually hits in the sense this replaced by a white, and this one is also gets replaced by white, and this one is also gets replaced by white. And because this portion is an actually white dots are there, I mean white pixels are there, that's why this one is also replaced by white. And coming here, because whenever we are placing this particular structuring element over this portion, this particular portion, this is actually the center. Because of this particular gaps of white pixels, this also gets replaced by the white. And this one also, whenever you can observe this particular operation of 3 by 3, and this also gets replaced by white. In this way, we can complete this particular operation of the concerned pixels, and this one also, just if you have considered this the operation of this, and the center pixel is also replaced by white. With this dots, wherever I am placing this red dots here, this all the pixels gets replaced by white. That means whites are increasing here and reducing the blacks. With increasing of whites, the size of this particular object gets reduced, and this one is also all these pixels gets replaced by whites, and all these pixels are also replaced by white, and here all these pixels are also replaced by white, and the leftover portion appears to be like this. This is an actually the structural element as a rectangle. Of course, here processing structuring element with this particular operation appears. This is an actually a resultant one. Padding behavior. Morphological functions position the origin of the structuring element. It's a center element over the pixel of interest in the input image. For pixels at the edges of an image, parts of the neighborhood defined by the structuring element can extend it past the border of the image. That is how you are going to perform these operations. These rules already were explained, we discussed already to some extent in the last slides. Pixels beyond the image border are assigned the minimum value offered by the data type. The binary images, these pixels are assumed to be set to 0. The grayscale images, the minimum values for unit 8 images, that means for 8-bit images, the minimum value is again 0. White pixels increases, black pixels decreases in case of dilation operation. White pixels, this particular point you should remember, white pixels increases and black pixels decreases. And for erosion, the operation is actually a reverse operation of the dilation. Pixels beyond the image border are assigned the maximum value offered by the data type. Maximum value in case of binary image is a 1. For grayscale image is 255. Black pixels increases and white pixels or decreases. Black pixels increases, white pixels or decreases in case of erosion operation, because it's a reverse operation of the dilation. These are the different examples of the dilation operation, and here it's not possible for you to explain these particular examples in examination. That's why I'm not explaining these particular things here, because it's prepared already on mathematical representation point of view. Not exactly this type of examples I have to explain in the exam, but still there is a possibility to show in the exam by your own the increasing of objects boundaries with this particular operation of dilation. This is one object and this is another object. We are representing these objects with the ones and maximum value of the binary and minimum values or zeros as a background. And this, if I have considered as a structuring element of template, all are ones, then doing the masking operation over the each and every pixel of this particular input image, in what way you are going to replace in this particular input image. Suppose if I have considered this center one here, it's an actually center one means this total 3, this all the pixels above the boundary of an input image to be considered as zeros. In this case, in this way, just you have to consider 3 by 3 pixels. So 1, 1, 1, 1, 1. This all the locations are actually zeros. That's why the center one is also 0 here. And if you move to the next point, next location in the sense like considering the center pixel as the second pixel of the first row, and that means this one. In this case also these 3 are zeros and this one is also 0. So if it is all are zeros means this one is also gets replaced by 0. And this way just this all the first row appears to be zeros only. Coming to the second row first one means here we are going to place this particular structuring element like this. If I have placed the structuring element here, this is the center one. So here there is no any pixels considered to be a zeros, and this all the pixels in this particular 3 by 3 are zeros, and there is no chance to overlapping with any of the pixel value of the structuring element. Then this one also 0. Coming to here and just extending this portion like this. Okay, this is the center pixel. The center pixel, all are zeros here. That's why this one is also 0. And there is no question of any one here. These 4 pixels of the input image appears to be 0, 0, 0, 0 only. Coming to the next location here, this one. And if I consider this is an actually 3 by 3 overlapping region. And here this one is mapping with this one. That is some matching. That means perfect match, something match and no match conditions. If we have consider the something match, because of this something match in the dilation operation, it leads to the actual value repeats here 1. That's why this particular portion is an actual, this particular third one, I mean second row, third pixel is replaced with the 1. That's why it's a 1. The same thing if you are doing on each and every pixel of the second row, this all the pixels gets replaced by 1. And whenever you are coming to this portion, this one is 1, 2, 3, 4, 5, 6, 7, 8, ninth, 8th second row, 1, 2, 3, 4, 5, 6, 7, 8, this one. And if you have, whenever you are placing the structuring element of 1, 1, 1 over this 0, 0, zeros, there is no question of any matching of any of these coefficients with this pixel values. That's why this center element to be replaced by 0 only. This is an actually 0 repeats here. Okay, in this way we can complete the process all the boundaries of the object, given object 1 and second object here. We can observe with this dilation operation both the objects extended its boundaries and overlapping, and here overlapping of these particular boundaries appears here. That is, whenever we go for the dilation operation, objects are closer to each other in case of dilation operation, but in case of erosion operation, that objects are actually making some gap in between the objects. White pixels increases and black pixels decreases. That's an actually the dilation operation we can observe here, increasing of white pixels with the binary notation of 1 as the maximum white value. This is another example with the dilation operation. This is an R and this is R, and this one is with the dilation operation, how we are replacing this R. G of xy is equals to, just we are representing 1 for structuring element hits F, otherwise 0. Based on this phenomenon only we have completed the dilation operation. Coming to the erosion, which is opposite to that, how we are denoting this erosion operation means F is an input image, S is the structuring element. F erosion with S is representing like this, produces a new binary image G is equals to F erosion with S. Once in all locations xy of a structuring elements, origin at which that structuring element S fits the input image F. That is, G of xy is equals to 1 if S fits F and 0 otherwise, repeating for all pixel coordinates xy. This is just opposite to the dilation operation. And in this, it's strings or thin objects in a binary image. Syntax of erosion operation is, for selecting of structuring element, SC is equals to image erode A of B. A is an input image, B is the structuring element. Output is 1 when element completely fits, or otherwise it's a 0. In this way, if you do the operation of input erosion operation over the input image, this is an input image and this is the structuring element. Here, after erosion operation, this is an actually input output image appears. That means this, if you have considered an object with the ones at the center, okay, this still this ones are appears to be minimized to only these 2 ones. That is, it thins the objects with this particular erosion operation. This is an example of input image, and this is actually processed. This is an actually the pre-processed image. Erosion of image F by structuring element S is given by F erosion of S. The structuring element S is positioned with its origin at xy, and new pixel values is determined using the rule. With this rule, this is an actually erosion image with the input image of R. This is another example. Original image binary image by thresholding, and with the structuring element of erosion operation, still each and every letter in this particular image becomes thinner as compared to the original image or as compared to the thresholding of a binary image. So erosion and dilation operations with completed. With this particular examples, we are in a position to understand the difference between, this is actually the example of erosion with the same example of dilation here explained. These are the two objects in the input image. Here we can observe with the same structuring element, if you do the erosion operation, how these objects are appears to be reducing the size and shape compared to the original images. This is the another example of a structuring element with the original image and processed image. This is the erosion operation. With the erosion operation, by placing the structuring element in these locations, wherever it is and actually matches, there we are going to consider the point, or otherwise just replacing the pixels by all or with the zeros. That's why it appears to be thinning the object in the erosion operation. So erosion and dilation, these are just an examples of with the square images, and wherever we are observing the large size of objects, with this particular operation, erosion we can consider this, and with the dilation we can enhance still the size of these larger objects with this particular dilation operation. This is another example of erosion and dilation operations. This is the original image, and A is the original image, and B to D, that is a BCD. Image erode using square structuring element of size 11 by 11. Structuring element 11 by 11 if you have chosen, this then actually the eroded image. And this one is 15 by 15 structuring element, and this one 45 by 45 structuring element. In these examples, what we are observing, the structuring element size increases means these particular objects which are appearing, those are reducing the size, and by reducing the size it disappears whilst increasing the size of the structuring element. Okay. These are the examples of differences between the erosion and dilation. Removal of structures of certain shapes and size given by structuring element. Filling of holes of certain shape and size given by structuring element. Erosion can split apart joining objects and strip away extrusions, and can repair breaks and intrusions. These are the differences of examples of objects here. Opening and closing we can see in the next session. In the next video we'll see the opening and closing operations. Now I'm winding off this particular session. I hope you are in a position to understand the erosion and dilation operations, basic operations of the morphological processing. Next session we'll see the opening and closing as a continuation of erosion and dilation operations. Thank you.